1101, Exam 5, review on chapters 12, 13, 14. All right, so this is the final exam for Physics 1101. And then after this, we'll have the final exam, which will be on December 9th in person. Okay, so I'll go through this as far as it's concerned, what might relate to this. For the lab, for this, chapter 12 on sound. This will also include lab 12, right, which is sound waves. Right, it goes directly with this. Some of the questions for the lab come straight from chapter 12. So we'll talk about this, so for that we have speed of sound. And our expressions for that are in chapter 12.1. So I've gone through the chapter 12 lecture. Characteristics sound, loudness, what characteristics of that, pitch, and so on, how are those related to amplitude and frequency as far as that are concerned. Okay. All right, moving on there, we got the decibel scale. Which again is given by beta is 10 log of I over I, what we call I naught, where I naught is the threshold of hearing, is 10 to the minus 12 watts per meter squared. So that is the decibel scale. Again, it's a logarithmic scale. I went through some of the examples related to that as far as this is concerned. Okay. All right, so I had examples there. All right. So on here, right, we have vibrations and resonance. So again, for a vibrating string, all right, again, this is more related to lab 11, the Meldis, where we had a vibrating wire, as far as that's concerned. All right, talked to nodes and antinodes and how those work. We have, so this is a vibrating string, we have sound tubes. And again, we had open tube, meaning it's open at both ends. And I had this from chapter 12. Again, the characteristics of this as far as for a open tube and a closed tube as far as the pressure, which would lead to this loudness. So you had open at both ends and closed at one end. And this is again related directly to lab 12, right? Resonance and sound tubes. So I went through those as far as, you know, what harmonics we have for an open tube. Harmonics are 1, 2, and 1, 2, and 3. Well, for a closed tube, it's 1, 3, 5, and so on. All right? So went through that. All right, then we had a quality sound a bit, as far as frequency, comparing a violin, piano, tuning fork. So, moving on from there, 12/6 beats, right? So if I have two different frequencies, say 440 and 442, all right, the beat frequency is the difference of the two, so the beat frequency would be 2 hertz, right? And you can detect this, so it has to be relatively close, as I talked about earlier. So if this is 440 hertz, which is concert A, 442, difference, beat frequency would be 2 beats, 2 hertz, as far as you'd say. Then the last part, section 12.7, is the Doppler effect, right? And again, we had the two formulas for either source and observer. All right, and the first case we have might be a siren either coming towards you or moving away. Or in the second case, so that was it, and this stays stationary, or in the second case, you have a source is stationary and the observer is either moving towards or away from the source. So you have the Doppler effect and the formulas from section 12.7, which I went over, the equations for doing that. And again, this is all based on the speed of sound is about 344 meters per second. All right. That's all I'm doing for chapter 12. As far as that's concerned, there's a short section on shock waves and sonic booms, meaning this is the speed of sound, and it's a limit for as far as that's concerned. Okay? So that's chapter 12. All right, moving on to chapter 13. Okay? And then what we have here, all right, chapter 13 on temperature. And what we call kinetic theory. All right, what we went through here, as far as this is concerned, we have the 3 temperature scales: Fahrenheit, Celsius, and Kelvin. All right, there's a conversion between Fahrenheit and Celsius. We're not going to be using that for this test. And again, conversion between Celsius and Kelvin is that Celsius is Kelvin minus 273, all right? And so we have absolute 0. So absolute 0 in the Celsius scale is minus 273 degrees. In the Kelvin scale, that is 0. All right? So that's the relationship between those two, and that's all we're going to. We'll be using the Kelvin scale for the gas laws. All right. We talked about thermal expansion. and that is delta L is L naught alpha delta T for linear expansion of solids. So this applies only to solids. And then we had delta V is V naught beta delta T for solids or liquids. But primarily for liquids, this is the expression here because we can't measure one dimension for solids. Talked a little bit about the characteristics of water, as far as what happens when it reaches the minimum point at 4 degrees Celsius, and it starts expanding. All right, if there are expressions needed for the test, I'll give you either alpha or beta. I won't say it, but I'll say which is which, as far as that's concerned. All right. So also in chapter 13, we have the ideal gas law. Which is PV is nRT. And what we're going to be using here is that pressure again is in atmospheres, volume is in liters, N is moles, T is in Kelvin, and R is the gas constant of 0.0821 as far as that's concerned. All right, so this is the expression we'll be using. And again, if you want, a cubic meter, 1,000 liters is 1 cubic meter, and 1 atmosphere is 10 to the 5th pascals, more or less. All right? So if you use the other one, that's the case there. All right. Okay, and then the last part here is on kinetic theory, KT, and that is the fact that we met the measurement of temperature, the kinetic energy, which is 1/2 mv squared, is given by, for a particular atom, 3/2 kT, where this is what we call the Boltzmann constant. So the kinetic energy is directly proportional to the temperature, or again, this is in degrees Kelvin. All right. And we had the distribution of molecular speed. So for a real gas, there's a distribution, or there's a peak. So if you have number and speed, not all of them are going exactly the same. There's some going less, some going less fast, but there's a peak, what we call the average speed of the gas. And this is independent of the type of gas, whether it's hydrogen, oxygen, or whatever. It's just all of them have the same temperature, but obviously a light molecule is going to go faster because it's a temperature, so it depends on the actual speed, depends on the mass of the molecule. All right, and that's all of chapter 13 we're going to do. We're not going to do anything as far as phases are concerned. So that's chapter 13. And then the final chapter, chapter 14, which is on heat. All right, again, kinetic relationship 4.186 joules is equal to 1 calorie, as far as that's concerned. All right, we got into that. We had the internal energy of a gas is given by U is 3/2 nRT, which will, again, we'll use this more later on in chapter 15 when we get into thermodynamics. So we talk about specific heat. All right, again, Q is mc delta T, or this is in grams. This is either degrees Celsius or degrees Kelvin, because change in temperature makes no difference. And C is 1 for H2O. All right, so this would be grams. So this is in calories per gram degree Celsius. So C is 1 for that. We did examples of mixing. We have latent heat, which again, we have Q is MLF, or latent heat of fusion or vaporization, where LF is 80 calories per gram for water, and latent heat of vaporization is 540 calories per gram for converting water to steam. Okay? And we have the examples of that. And, okay, all right, so that's the main part. And then the last part, leaving this up here, is I get heat transfer. All right, conduction, convection, and radiation. And I went through the examples. The only one where we have a real qualitative number is the power radiated is proportional to the temperature to the 4th power, where this is in degrees Kelvin. So if you double the temperature, the power radiated will be to the 2 to the 4th, which would be 16. So I went through those, what are the characteristics of each of these as far as what's actually happening in this kind of heat transfer. Because we have heat goes from hot to cold from the first law of thermodynamics. And that is it for exam 5. All right, so that's the end of the content for the semester. I will send an email out as far as what will be, the final will just be comprehensive over all 5 exams. Again, I'll be dropping the lowest exam score in determining grades. And again, as I say, you'll be able to use for the final is 5 sheets of paper, front and back, with whatever you want to write on it, equations and so on. If you want to email me for questions on stuff, I can help you, but otherwise I would just take all the equations, stuff we've used during the semester, write them down, put down some labels and what all the equations mean, what chapter they're from, so organize them. Don't just have a list of random equations, because that'll make it complicated. So I'll send emails out regarding the final is concerned. All right, again, the final exam 5 opens on December 1st and will close on the 6th. So have a good